When Earth nearly died, the day 98% of life vanished. Full documentary. Beneath a blood-red sky, the world trembled as firestorms and poisonous clouds swept across Pangaea. Oceans boiled, forests ignited, and the air itself turned lethal, signaling the collapse of ecosystems that had thrived for millions of years. The Permian Earth teetered on the edge of annihilation, a planet gripped by forces beyond any creature's comprehension. In a single, catastrophic span, nearly 98% of life vanished, leaving scars in rocks, sediments, and fossils that whisper the story of extinction. Join us as we descend into this apocalyptic moment, tracing the final pulses of a world forever transformed. The lost world before the fall. Twilight draped the Permian landscape in crimson haze, and for a fleeting span of geological time, life stood at its zenith. Across Pangaea, glossopteris forests stretched unbroken across the horizon, their leathery leaves stirred by dry winds sweeping over dunes the size of cities. Rivers meandered through floodplains lined with towering cordaites, their root systems binding the soil into fragile equilibrium. Amphibians the length of small cars lingered near the water's edge, their glossy skin glinting under a sun already harsher than it had been eons before. The Earth, 252 million years ago, seemed eternal in its vitality, a planet rich with oxygen, thriving in a deceptive calm before its deepest convulsion. Across the interior deserts of Pangaea, the climate was unrelentingly seasonal. Monsoon rains flooded the lowlands into temporary seas, then retreated beneath blistering heat that cracked the ground into hexagonal scars. Fossilized mudstone layers preserved the rhythmic alternation of wet and dry, each stratum a pulse in the planet's environmental heartbeat. Paleosol analyses reveal high iron oxide content, a mark of prolonged droughts that tested the resilience of flora and fauna alike. Yet adaptation flourished. Thick-skinned seed ferns, drought-resistant conifers, and hardy lycopsids colonized the margins where few plants could persist. Their existence a quiet defiance against geological instability that even then whispered from below. Through the forests moved the apex hunters of their age, the gorgonopsids. Their saber-like canines, some exceeding 15 centimeters, gleamed like ivory blades as they stalked dicynodont herds through the undergrowth. These predators were not reptiles, but therapsids, distant relatives of mammals, their skulls showing the first hints of warm-blooded metabolism. Oxygen isotope studies from fossil bone phosphate suggest they may have maintained internal temperatures higher than the ambient air, an evolutionary prelude to what mammals would later perfect. Each gorgonopsid strike was swift and deliberate, a predator born of ecosystems at their most complex and fragile. In the marshlands and river deltas, Diplocaulus and Eriops thrived massive amphibians with sprawling limbs and labyrinthine skull bones. Their lungs and gills allowed them to inhabit both water and air, bridging evolutionary eras still in transition. The sheer diversity of these ecosystems, from highland conifers to coastal swamps, represents one of the most ecologically complex intervals in Paleozoic history. Every niche was filled, every balance delicately maintained, every species unaware of the geological clock winding toward catastrophe. Far to the north, near what would become Siberia, volcanic rumblings had not yet broken the crust, but magma plumes swelled in the mantle, raising the surface imperceptibly. Geophysical models estimate that heat flow in certain regions increased by nearly 20% during the final few million years of the Permian. This subtle warming shifted atmospheric circulation, amplifying droughts in continental interiors. Dust trapped in ancient sediments reveals rising concentrations of nickel and chromium traces of deep mantle material already finding pathways upward. Dimetrodon ruled the land, its sail capturing morning sun and shedding midday heat. Though long extinct by the very end of the Permian, its descendants, the therapsids, carried its metabolic legacy forward. Skeletal microstructure shows vascularized bone tissue, evidence of accelerated growth rates and internal temperature regulation. These were not sluggish, cold-blooded reptiles, but pioneers of endurance, testing physiological limits in a climate already beginning to change. As CO2 levels slowly climbed toward 1,000 parts per million, a threshold identified in trapped gas bubbles within ancient halite ecosystems, adjusted through necessity rather than foresight. The seas bordering Pangaea told a parallel story. Reefs of sponges and calcareous algae thrived in shallow seas, their structures alive with ammonites, brachiopods, and crinoids. Each reef was an underwater metropolis, engineered by slow, chemical labor, calcium carbonate precipitated molecule by molecule in clear, warm waters. Yet even in these tranquil depths, chemical warning signs begin to emerge. Strontium isotope ratios in late Permian limestones show subtle deviations, signaling changes in ocean circulation and continental weathering. These minute geochemical shifts, invisible to the creatures themselves, were the early tremors of a planetary imbalance that would soon collapse the very chemistry of life. Insects, too, had reached evolutionary triumph. Winged giants spanned the skies, and their mandibles left distinct feeding traces on fossilized leaves, marking co-evolutionary dances between predator and plant. Some of these trace fossils, preserved in South Africa's coal seams, record entire communities of pollinators, predating flowering plants by over 100 million years. The complexity of these interactions reveals a biosphere at peak efficiency energy cycling through trophic levels with little waste. It was a golden equilibrium, but one delicately poised on a foundation of climate, oxygen, and stability that was already shifting beneath their feet. Along the edges of Pangaea's supercontinent coastlines, shallow lagoons evaporated under relentless heat. Evaporite deposits in what is now China and the Middle East preserve halite crystals formed during extended arid intervals. These minerals, when analyzed, contain microbubbles of ancient air, tiny archives, revealing atmospheric composition. Oxygen levels hovered near 25%, the highest since the Carboniferous, sustaining enormous animal sizes and rapid metabolic rates. But such oxygen abundance also rendered the world vulnerable to fire. Fossil charcoal layers become increasingly frequent in late Permian sediments, a clue that wildfire frequency was rising. Even the polar regions were not immune to change. In the southern high latitudes of Gondwana, once lush fern forests began to thin. Glacial deposits had long receded, replaced by seasonal wetlands and silt plains rich in vertebrate fossils. Paleobotanical evidence from Antarctica shows decreasing diversity in glossopterid flora, possibly linked to subtle yet persistent temperature increases. The world's thermal gradient, once stabilizing ocean currents, weakened, setting the stage for stagnant waters and oxygen depletion in the millennia ahead. Time, in this ancient world, flowed not as hours, but as slow breaths of continents and oceans. Each species, from armored parasaurs lumbering through the underbrush to shimmering ammonites drifting through the seas, was a note in Earth's intricate harmony. Fossilized burrows, coprolites, and leaf impressions all attest to a biosphere humming with activity, its diversity unmatched until the Mesozoic. Yet within these layers lies a pattern of stress, thinning growth rings in fossilized wood, declining carbonate deposition rates, subtle but accelerating. The signs of strain were accumulating quietly, each one an imperceptible step toward annihilation. In the calm before destruction, the earth appeared content, but its balance was illusory. Beneath the forests, pressure mounted in magma chambers. Above them, the atmosphere thickened with greenhouse gases. Evolution, blind to its own fragility, continued to elaborate complexity upon instability. In that grandeur lay both triumph and tragedy, a planet at the height of its creative power, teetering unknowingly on the threshold of ruin. Soon, the first fractures in this splendid world would open, and through them, the age of fire would begin. The cracks beneath the surface. Beneath the tranquil plains of Pangaea, the world's foundation began to stir. The mantle shifted like an immense, slow tide, unseen yet irresistible, breathing heat through fractures deep within the crust. Above, the surface remained deceptively calm, forests swaying, rivers gliding, amphibians basking in the ancient sunlight, while far below, a colossal reordering of energy was underway. Earth was drawing a deep breath, and its exhalation would change everything. Miles below the forests, rock moved like breath, slow and unceasing. Convection currents carried molten silicate upward in vast, spiraling plumes, rising from depths where temperatures exceeded 3,000 degrees Celsius. These ascending columns of heat were not sudden anomalies, but the culmination of millions of years of gradual imbalance, the mantle's way of releasing built-up tension. The lithosphere, thin compared to the planetary body it floated upon, began to stretch and crack under the strain. In this unseen realm, continents were both passengers and casualties of a restless interior. From the margins of the supercontinent, seismic murmurs travelled inward, faint but relentless. The landmass of Pangaea, though immense, bore the cumulative stress of tectonic collisions that had built it. Each boundary, once forged in continental union, has now become a site of vulnerability. Faults propagated like invisible lightning across what is now Siberia and northern China, fracturing the crust along lines hundreds of kilometers long. Geologists mapping these ancient structures today find intrusive sills and dikes, narrow veins of basalt cutting through coal seams, and sandstone silent witnesses to magma that once sought escape. Within the mantle, heat pooled in rising columns, plumes that pressed hungrily against the lithosphere above. Petrological analyses of ancient basalts from the Siberian traps reveal high nickel and chromium content, elements characteristic of deep mantle origin. Isotopic ratios of helium, xKe, He, within these rocks exceed values typical of mid-ocean ridge basalts, confirming that the magma emerged from Earth's lower interior, not from shallow melting. This was no ordinary volcanism, it was planetary exhalation, a wound opening from within. The crust thickened in response, doming upward like the surface of a boiling pot, as magma chambers accumulated beneath thousands of kilometers of desert plain. Each chemical signature, locked in ancient minerals, tells of a planet under mounting stress. Zircon crystals, microscopic but eternal, retain isotopic records of rapid thermal fluctuations, a pattern consistent with repeated magma intrusion. Uranium lead dating places the first major pulse of this activity around 252.3 million years ago, mere tens of millennia before the global die-off that would erase nearly all life. In geological terms, that is, an instant, the blink before catastrophe. Beneath the sediments of what would become Siberia, magma gathered in reservoirs whose volumes dwarfed modern oceans, their pressure building with inexorable precision. In laboratory thin sections of basalt glass, scientists today glimpse that ancient pressure frozen mid-motion under polarized light. Trapped gas bubbles shimmer like galaxies, remnants of volatile release during crystallization. These gases, carbon dioxide, sulfur dioxide, methane, were the volatile breath of the planet, locked for eons and now mobilized. Each eruption, even before the great outpouring began, exhaled millions of tons of carbon into the atmosphere, yet the full flood was still to come. For now, the magma chambers grew in silence, sealed by layers of overlying rock, their contents swelling toward the inevitable rupture. Gravity itself participated in the unfolding drama, drawing magma upward through zones of weakness in the crust. Numerical models of mantle convection show that such plumes not only ascend vertically, but also spread laterally, infiltrating fault systems and sedimentary basins. Where these intrusions met coal-rich strata, contact metamorphism ensued, releasing methane in quantities sufficient to alter the climate on a global scale. In the Norilsk region of Siberia, drill cores reveal blackened, carbonized seams where coal once lay a testament to this subterranean combustion. The air above those buried fires would soon thicken with poison. Under the region that would become Siberia, magma accumulated into chambers larger than modern seas. Some geophysical estimates suggest the volume of erupted material eventually surpassed 4 million cubic kilometers, enough to bury the entire continental United States under a kilometer of rock. Before eruption, these reservoirs pulsed with liquid fire, temperatures exceeding 1,500 degrees Celsius, dissolving minerals, fusing crustal fragments, and generating colossal quantities of gas. The pressure they exerted was immense, measurable today in the deformation of ancient rock fabrics and the tilt of preserved strata. Each pulse of magma represented a heartbeat in the planet's slow, feverish build-up to destruction. Geophysical reconstructions reveal crustal doming across thousands of kilometers, the skin of the planet swelling like breath before eruption. This deformation uplifted the land by hundreds of meters, altering drainage patterns and isolating entire basins. Sedimentary records show rivers redirected, lakes drained or formed anew, and erosion rates spiked the landscape itself, warping under invisible hands. In the fossil record, this distortion appears as an interruption, ecosystems abruptly displaced, environments transformed within a single geological layer. The surface world, still vibrant, was unknowingly reacting to the movements of magma miles beneath its roots. Even at the surface, faint omens appeared, fissures exhaling warmth, minerals discoloring stream beds, air thickening with the scent of sulfur. Hydrothermal vents erupted in what were once forests, encrusting fallen logs with silica. Shallow aquifers boiled from below, leaving mineral crusts that shimmered in the sun. The temperature of nearby soils rose, sterilizing seeds and burrows. Volcanic gases leached into groundwater, lowering pH levels and disrupting the fragile chemistry of life. These subtle signals were the planet's warning, the tremors before a great release. Deep below the seeming calm, the interplay of pressure and temperature crossed an irreversible threshold. The longer the magma remained trapped, the more gases accumulated. Pressure thresholds, once elastic, hardened into inevitability. Within mere thousands of years, a blink between one geological age and the next, the crust would yield. Sills and dikes would widen, the surface would rupture, and the greatest volcanic episode in Earth's history would begin. But at this moment in the story, the surface still slept. In that buried silence, Earth crossed an invisible threshold, one from which there was no return. What began as slow convection now bordered on explosive transformation. Deep within, the mantle plume that had taken millions of years to form was about to reach its destination. The planet's pulse quickened, though no creature could hear it. Soon, the first fountains of basalt would rise through cracks in the crust, igniting forests, darkening skies, and beginning the sequence that would unmake nearly all life. The calm before the fire was ending, and the world itself was preparing to tear open. Fire without end. Molten rivers surged across the Siberian landscape, swallowing forests and plains alike in an unstoppable tide of basalt. Trees were incinerated before they could fall, their trunks blackened and warped, leaving charcoal layers that mark the first violent pulses of the Permian's final chapter. Lava sheets, often more than a kilometre thick, advanced with a terrifying, almost liquid persistence, consuming everything in their path. Across thousands of kilometres, this infernal tide reshaped the supercontinent's topography, filling valleys, diverting rivers, and burying soils rich with life. Each advance was slow in human terms, but catastrophic in geological consequence, a flowing monument to the planet's fury. Blackened skies reflected the glare of flowing basalt, turning day into a distorted twilight. Plumes of smoke and ash rose tens of kilometres, obscuring the sun and casting shadows that stretched over thousands of square kilometres. Atmospheric circulation carried particulate matter across Pangaea, dropping fine volcanic dust into distant oceans and continents. Sediment cores from South China and Australia reveal repeated layers of tuff, evidence of eruption pulses spanning centuries, if not millennia. In these layers, geochemists identify sudden spikes in mercury and trace metals, a fingerprint of Siberia's relentless volcanic activity. The air itself became a medium of destruction, altering the climate long before life was directly consumed by lava. Each eruption released more gas than the entire modern industrial output over centuries, saturating the atmosphere with carbon dioxide, sulfur dioxide, and methane. Models estimate CO2 concentrations soared beyond 8,000 parts per million, far surpassing levels seen in the modern anthropogenic record. Sulfur aerosols reflected sunlight, causing short-term cooling in some regions, while long-lived greenhouse gases triggered global warming over centuries. Acid rain formed as sulfur dioxide combined with atmospheric moisture, lowering soil and freshwater pH, corroding plant tissues, and stressing even the hardiest Permian flora. Fossilized leaves show signs of chemical burns and decay consistent with these acidic deluges, a silent record of invisible atmospheric assault. Pillars of smoke and ash rose into the stratosphere, forming clouds that circled the globe. Within weeks, these clouds reduced sunlight, suppressing photosynthesis and triggering the first waves of ecological collapse. Marine life felt the impact indirectly. Surface waters cooled temporarily, while deeper waters remained stagnant and hypoxic. Microfossils in early Triassic sediments record anomalies in planktonic populations, signaling disruption to the marine food web. Coral reefs, already under environmental stress, show evidence of bleaching and mortality coincident with ash deposition, demonstrating that the eruption's reach extended far beyond Siberia itself. In shallow seas adjacent to eruptive zones, water temperatures climbed rapidly, stressing delicate marine ecosystems. Thermally induced stratification limited oxygen exchange, intensifying anoxic conditions that would become widespread during the extinction. Sedimentary layers rich in pyrite and organic carbon indicate persistent auxinia hydrogen sulfide accumulation, lethal to most marine life. These chemical signatures are mirrored in terrestrial sediments, where coal seam oxidation and charcoal beds chronicle fires, heat, and toxic fallout that together created an almost unbreathable environment for land-dwelling creatures. Geochemical analyses reveal that pulses of lava released extraordinary quantities of mercury, providing a global tracer of Siberian traps volcanism. Mercury anomalies found in marine and terrestrial sediments thousands of kilometers from the eruption site confirm the reach of these events. Carbon isotope excursions, delta to the power of 13c, demonstrate massive perturbations in the carbon cycle, consistent with the addition of volcanic CO2 and methane into the atmosphere. Even plants that survived initial lava inundation were chemically stressed, their growth rings narrowing and their reproductive capacity diminished. Evidence of an ecosystem already gasping under invisible pressure. Volcanic CO2 and methane amplified greenhouse warming, pushing global temperatures toward extremes unseen for millions of years. Paleoclimate reconstructions indicate polar temperatures rose by 10-15 degrees Celsius, while equatorial regions reached levels hostile to most large terrestrial vertebrates. Oxygen levels in shallow waters declined, compounding heat stress and acidification, while hypercapnia challenged the respiratory systems of amphibians and early synapsids. Fossils from this interval show stunted growth and skeletal anomalies in surviving species, a biological testimony to the planet's slow suffocation. The landscape became unrecognizable, rivers buried under lava, forests charred beyond recognition, the air thick with toxic miasma. In the coal basins of Siberia, paleosol layers are blackened and sterilized, bearing chemical scars of extreme heat and acidification. Burrows, nests, and trace fossils abruptly vanish in these layers, indicating sudden mortality of terrestrial communities. In the oceans, the first signs of mass die-offs appear as condensed shell beds and monospecific fossil assemblages, a warning of total collapse. Life that had thrived for millions of years now faced the combined fury of fire, poison, and a suffocating climate. Even now, basalt flows exceeding a kilometre-thick stand as silent monuments to a day the planet seemed to burn without end. Modern measurements of eruptive volume and duration underscore the unparalleled scale. Millions of cubic kilometres of molten rock released over roughly 1 million years. The Siberian Traps eruptions became both the trigger and amplifier of the greatest extinction in Earth's history. Yet, as catastrophic as these events were, their deadliest effects were not always immediate. The gases and climate perturbations would continue to poison oceans and air long after the lava cooled, ensuring that life's decline was drawn out, inexorable, and nearly total. The firestorms of Earth's crust had begun, and with them came the first suffocating veil of poison across the planet. Lava and gas transformed the world into an inferno, signaling that the equilibrium of life would no longer hold. Above and below, every ecosystem, every species, every living connection felt the reach of these eruptions. The air itself became lethal, carrying ash and toxic gases across continents, suffocating forests and corroding rivers. Life gasped under a sky turned deadly as the poisonous veil spread relentlessly, reshaping the very atmosphere that had once sustained it. The sky turns to poison. The horizon darkened as ash and gas hung thick in the atmosphere, blotting the sun in a relentless, suffocating veil. What had once been clear skies now shimmered with suspended particles, a turbulent mixture of sulfur aerosols, carbon dioxide, and volcanic dust. Light filtered through this haze in muted, sickly tones, casting shadows that trembled across charred forests and rivers coated in ash. The air itself carried a latent menace, a chemical hostility, invisible yet undeniable, touching every leaf, every creature, every breath. Across the supercontinent, living beings felt an insidious change before it manifested in outright catastrophe. Rain no longer fell as a gentle blessing, but as corrosive droplets, scouring the land with relentless acidity. Sulfur dioxide from countless eruptions reacted with water vapor to form sulfuric acid, while halogens and other volcanic gases exacerbated the chemical onslaught. Geochemical analyses of paleosols reveal layers leached of essential minerals, evidence of acidic washout that stripped nutrients from the soils. Forests show dieback in the fossil record, leaves etched with microscopic damage, and root systems unable to recover. Across river basins and lowlands, aquatic systems were altered in parallel, the first hints of a planetary suffocation that extended beyond terrestrial life. Volcanic aerosols combined with water vapor to form clouds acidic enough to corrode even resilient flora. Trees with thick bark and hardy leaves displayed stunted growth rings, indicating repeated exposure to chemical stress. Insects, sensitive to both precipitation chemistry and ultraviolet radiation, suffered massive die-offs, evidenced by abrupt declines in their fossil traces. Sedimentary layers capture these events with remarkable fidelity. Blackened soil horizons, interspersed with thin ash layers, document a cycle of acid rain and partial recovery, repeated over centuries yet progressively intensifying. Every drop of rain now carried the weight of invisible death. Paleosol layers reveal chemical imprints of extreme acidification across continents. Aluminum, calcium, and magnesium were leached from soils, altering pH and leaving a barren substrate incapable of sustaining the dense Permian forests. Plants reliant on nutrient-rich soil perished, creating cascading effects for herbivores and their predators. Even in regions far from eruptive centers, these changes left a measurable signature, proving that atmospheric toxicity was truly global. These soils, frozen in time as a geological record, tell of Earth's slow suffocation, a chemical warfare waged invisibly, yet with deadly effectiveness. Ozone depletion allowed bursts of ultraviolet radiation to reach the surface, battering exposed life with relentless intensity. Fossil leaves show patterns of cellular necrosis consistent with high UV exposure, and paleontologists observe stunted growth and abnormal morphologies in terrestrial vertebrates. This influx of radiation compounded the effects of acid rain, weakening defenses, impairing reproduction, and pushing ecosystems toward collapse. The sky itself had become both furnace and razor, baking and slicing life simultaneously. Across Pangaea, the planet's breath, once a source of sustenance, turned indiscriminately lethal. Trees show evidence of sunburned leaves, microscopic damage etched into their cellular structures. Insects trapped in amber or preserved in sedimentary layers display deformations consistent with UV-induced stress, corroborating chemical and radiative damage. Amphibians, particularly those dependent on freshwater environments, experienced stunted growth and increased mortality. Fossil assemblages record sudden declines in diversity, coinciding with peaks in sulfur and mercury deposits, which act as temporal markers linking atmospheric catastrophe to ecological decline. Every organism, from the smallest beetle to the largest dicynodont, became a witness to a world slowly poisoned. Marine life felt the atmosphere's suffocation indirectly, as acid rain altered river chemistry and subsequently ocean pH. Rivers carried dissolved sulfates and acids into shallow seas, preconditioning them for widespread anoxia. Calcium carbonate precipitation in shells and reefs slowed, leaving marine organisms vulnerable to chemical dissolution. Microscopic plankton, the base of oceanic food chains, were among the first casualties, their mass mortality recorded as condensed microfossil layers. These subtle shifts in marine chemistry presaged the catastrophic oceanic collapse to come, demonstrating how the atmosphere's toxicity rippled through every ecosystem. Isotopic anomalies in carbon and sulfur reflect rapid injection of gases into the air, measurable millions of years later. Delta to the power of 13c excursions indicate massive CO2 release, while delta to the power of 34s shifts reveal widespread sulfur mobilization. These geochemical fingerprints, now preserved in sediments from all corners of the globe, corroborate the timing and magnitude of Siberian Traps eruptions. They provide a precise timeline for how volcanic activity translated into atmospheric transformation, confirming that the air itself became a lethal agent capable of decimating life both on land and in the oceans. Fossilized insects and amphibians display stunted growth and mortality, corresponding with atmospheric toxicity. Burrows are abandoned, eggs fail to hatch, and the intricate web of Permian ecosystems unravels before it can adapt. Even species adapted to heat or drought found no refuge from acidic precipitation and ultraviolet exposure. The combined assault of chemical and radiative stress created a planetary bottleneck, compressing evolutionary pressures into a period of unparalleled intensity. Every breath, every drop of water, every moment of daylight became fraught with lethal consequence. Storm systems transported acidic clouds across Pangaea, leaving ecological devastation in their wake. Sediment cores reveal repeated acid pulses, sometimes separated by decades, sometimes by mere years. Each pulse left its mark: stripped soils, dying forests, depleted lakes, and stressed fauna. The planet's surface became a theatre of chemical warfare, driven not by intent, but by the unstoppable interplay of lava, gas, and water. Life endured only in pockets, fragile refuges, where conditions remained marginally tolerable, a precarious foothold in a world increasingly hostile. Even in remote regions, chemical signals of atmospheric change are recorded in sediment cores and mineral veins. Mercury spikes, sulfate layers, and isotopic anomalies appear on every continent, confirming the global nature of the crisis. No ecosystem remained untouched. From equatorial swamps to high-latitude wetlands, life encountered the same slow suffocation. The very breath of the earth had turned dangerous, and all who depended on it struggled to survive. The sky, once a source of life and vitality, had become a conveyor of slow, pervasive death. Acid rain, UV radiation, and poisonous gases combined to reshape ecosystems, preparing the stage for the ocean's collapse. From the poisoned skies above to the dying seas beneath, the planet teetered on the brink, a world in which survival was no longer guaranteed. Life held on in fragments, shadows of its former abundance, as the lethal legacy of the atmosphere seeped into every current, every tide, suffocating the fragile marine biosphere in its deadly embrace. The oceans lose their breath. The seas grew still, their once lively waves carrying only whispers of what had thrived within. Shimmering shoals of trilobites, vibrant ammonites, and intricate coral reefs that had dominated the late Permian waters now existed only in memory, their skeletal remains scattered across sediment beds. Surface currents, once energetic and oxygen-rich, faltered under the weight of warming, acidic waters. The ocean's breath, a lifeline that had supported complex ecosystems for millions of years, began to fail, leaving silent expanses where abundance once pulsed. Trilobite fossils, once abundant, lay fragmented and disordered in layers of fine sediment, their disappearance marking the early signs of a marine apocalypse. High-resolution stratigraphic studies reveal condensed horizons filled with skeletal debris, indicating sudden population collapses. In these early dead zones, opportunistic bacteria proliferated, decomposing the remains of organisms and releasing further carbon into the water. The balance of nutrients shifted catastrophically, disrupting food webs and destabilizing communities from plankton to apex predators. Each layer tells a story of gradual suffocation, yet the scale of devastation was global and relentless. Oxygen levels dropped in the deeper waters, creating invisible dead zones where life could no longer persist. Redox-sensitive trace metals preserved in sediment cores, including molybdenum, uranium, and vanadium, show widespread anoxia extending from coastal shelves to the abyssal plains. Iron speciation patterns further confirm persistent oxygen depletion, indicating that even surface layers were intermittently stressed by hypoxic events. Marine vertebrates, reliant on dissolved oxygen, faced both acute and chronic challenges, while mobile species attempted, often unsuccessfully, to relocate to more hospitable waters. Rising temperatures altered stratification, isolating surface waters from deeper layers and trapping heat below. Paleothermometric data reveal that equatorial sea surface temperatures exceeded 35 degrees Celsius, while subsurface waters warmed more slowly but remained lethally hypoxic. The thermal barrier prevented vertical mixing, cutting off nutrient cycling and exacerbating oxygen depletion. Planktonic organisms, the foundation of the marine food web, suffered massive die-offs. Without them, filter feeders and higher trophic levels began a domino-like decline, culminating in an unprecedented collapse of marine productivity. Coral reefs began to bleach and crumble, leaving skeletal husks as monuments to sudden decline. Fossilized reef frameworks show abrupt terminations, with dead coral interspersed with ash layers from Siberian Traps eruptions. High-resolution microscopy indicates partial dissolution of aragonitic structures, a result of acidification from volcanic CO2 and sulfuric acid deposition. Reef-associated fauna, including brachiopods and bivalves, vanished in tandem, demonstrating the interconnected vulnerability of complex marine habitats. What had been flourishing ecosystems for tens of millions of years now faced irreversible collapse. Sediment cores reveal layers rich in organic carbon, evidence of mass die-offs and bacterial decomposition. These black shale deposits accumulated rapidly, reflecting both the abundance of decaying biomass and the stagnation of water columns. Hydrogen sulfide, a byproduct of bacterial sulfate reduction, increased in concentration, producing a toxic chemical layer that further prevented recovery. Isotopic analyses of delta to the power of 34S and delta to the power of 13C show repeated excursions coinciding with pulses of Siberian Traps volcanism, confirming a tight coupling between atmospheric and marine crises. Ammonite shells, once flourishing, accumulated in dense horizons marking ecological collapse. Their disarticulated fragments provide both a record of mortality and an insight into the speed of environmental deterioration. Some ammonite species, resilient to minor stressors, persisted in isolated refuges, but overall diversity fell by more than 90%. Similar patterns appear in bivalves and gastropods, revealing that the collapse was not selective but nearly total. These fossil records serve as a testament to the ocean's sudden loss of breath and the global reach of the crisis. Anoxic conditions produced hydrogen sulfide, detectable in isotopic signatures that trace the deadly progression. Sulfide poisoning would have been particularly lethal to shallow water organisms, further eroding the stability of near-shore ecosystems. Paleontologists identify microbial mats and black shale horizons associated with these events, indicating areas where life was extinguished rapidly. The oceans, which had once been teeming with vibrant and complex ecosystems, were now chemically suffocating. a slow but unstoppable rot from within. Marine plankton declined sharply, removing the foundation of oceanic food webs and amplifying systemic collapse. Foraminifera and radiolarians, vital to carbon cycling, dwindled in both abundance and diversity. Without these microscopic organisms, nutrient recycling faltered, reducing primary productivity and triggering cascading failures throughout the food chain. Predator species, from large fish to early marine reptiles, experienced population crashes as their food sources vanished. By the end of these pulses, the oceans resembled a vast, silent grave, hiding only fragments of their former vitality. Even shallow seas, connected to rivers carrying acidic runoff, succumbed to chemical stress. Waters that once supported abundant life became corrosive, their pH lowered by volcanic gases transported from the continents. Freshwater influxes carrying dissolved sulfates and metals compounded the problem, affecting estuarine species and coastal fisheries. The interconnectedness of terrestrial and marine systems meant that land-based environmental stressors directly amplified oceanic collapse, demonstrating the full planetary reach of the Permian catastrophe. Examined closely, fossilized fish reveal stunted growth, skeletal deformities, and signs of physiological stress consistent with hypoxia. Examination of vertebrate otoliths and bone microstructure reveals episodes of metabolic strain, interrupted growth, and early mortality. These biological signals, preserved across multiple continents, corroborate geochemical evidence of low oxygen levels, rising temperatures, and chemical toxicity. Even the most mobile and adaptable marine animals were unable to escape the slow suffocation of their environment. From the deep trenches to coastal lagoons, the oceans were losing the breath that had sustained life for millions of years. Surface productivity collapsed, deep waters became toxic, and the intricate web of Permian marine life unraveled almost completely. The oceans, once a cradle of biodiversity, became a reflection of the poisoned skies above, a mirror of the planet's collapse. Life clung desperately to refuges, struggling both in water and on land, setting the stage for a final chapter of terrestrial struggle and near-total extinction. The silent seas now whispered warnings to the world above, a portent of the mortal struggle awaiting life on land. As oxygen vanished and heat intensified, both oceans and continents became arenas of survival against impossible odds. On the scorched continents, the last remnants of terrestrial life clung to existence, each breath a fight, each step a defiance against a world already unrecognizable and teetering on the edge of annihilation. Forests of ash and dust, embers glowed across once vibrant forests, smoke curling into a darkened sky, a haunting veil over landscapes that had thrived for millions of years. The towering Glossopteris and Cordytes, once stretching like living cathedrals toward the sun, now smouldered in silent ruin. Volcanic gases from the Siberian traps mingled with the heat of spontaneous fires, creating an infernal synergy that consumed leaves, bark, and wood alike. Charred trunks stood like monuments to a vanished age, their skeletal forms etched against ash-laden skies, signalling the beginning of terrestrial annihilation. Rivers that had carved fertile valleys ran dry, leaving cracked beds beneath a merciless sun. Water levels plummeted as volcanic activity disrupted precipitation patterns, and heat waves intensified evaporation. Floodplains that once nourished diverse amphibians and early synapsids became barren stretches of dust and salt. Fossilized river channels reveal sediment collapse and desiccation features, painting a picture of a hydrological system under siege. Aquatic life, already stressed by acid rain and warming, dwindled further as freshwater refuges disappeared entirely. Soils turned to dust under repeated acid rain and heat, unable to sustain even the hardiest plants. Geochemical analyses show leached calcium, magnesium, and potassium, stripping the substrate of nutrients essential for photosynthesis. Even hardy pioneer species could not establish themselves, leaving vast tracts barren. Wind scoured these desiccated plains, carrying ash and dust across hundreds of kilometers, burying surviving flora in suffocating layers. These nutrient-starved soils compounded the biological collapse, demonstrating how chemical, thermal, and hydrological stresses combined to dismantle terrestrial ecosystems. Charcoal layers record the firestorms that swept across Pangaea, leaving skeletons of trees behind. Across sedimentary deposits from Russia to China and South Africa, microscopic and macroscopic traces of burning are preserved, marking multiple pulses of wildfire activity. Each layer tells of repeated cycles: ignition, consumption, and smothering of plant life, leaving behind nothing but ash and carbonized remnants. Fires were not isolated. They coincided with volcanic eruptions, demonstrating how tectonic activity amplified natural ignition, creating a feedback loop of destruction across the supercontinent. Leaves and stems, scorched and fossilized, mark the rapid collapse of photosynthetic life. Cuticles show cellular breakdown consistent with extreme heat and chemical stress, while petrified roots reveal stunted growth before death. Paleoecologists note abrupt declines in plant diversity, with specialized species disappearing first, unable to tolerate the combined effects of fire, acidification, and drought. This sudden loss of vegetation initiated cascading effects, beginning with herbivores whose survival depended entirely on these plants. Herbivorous synapsids and amphibians faced starvation as their food sources vanished. Dicynodonts, periosaurs, and giant amphibians show evidence of malnutrition and interrupted growth in fossilized bones. Fossil assemblages reveal abrupt declines in population density, suggesting many species perished within a few generations. Those that survived likely faced increased competition for meager resources, creating a brutal natural sieve through which only the most adaptable individuals could pass. Predators, in turn, suffered from the disappearance of prey, their populations plummeting. Large gorgonopsians and other apex predators, once dominant across the Permian landscapes, left fossil evidence of stunted individuals and mass mortality layers. The collapse of the lower trophic levels reverberated upward, illustrating a cascading extinction effect that left even top predators vulnerable. Each disappearance amplified the instability of remaining ecosystems, pushing the terrestrial world toward near-total collapse. The preserved footprints halt suddenly, a silent testament to animals that perished before reaching their destination. Impressions of limbs frozen in sediment or footprints that never resume reveal the suddenness of mortality events. These biological snapshots suggest that animals died where they foraged or travelled, unable to escape fire, heat, or starvation. Across continents, similar patterns emerge, a grim testament to the global scale of the disaster. Ash deposition altered soil chemistry, compounding drought and chemical stress. Fine particles from volcanic eruptions and fires coated the landscape, inhibiting photosynthesis and further leaching nutrients from already impoverished soils. The combination of heat, dust, and chemical insult created inhospitable conditions that persisted for centuries, delaying recovery and creating feedback loops of ecological degradation. Surviving flora and fauna were confined to isolated refuges, precariously clinging to life as their environments deteriorated around them. Plant microfossils reveal a sudden decline in diversity, with specialized species disappearing first. Spore assemblages, pollen counts, and leaf cuticles show abrupt shifts in composition, indicating the preferential loss of sensitive taxa. Generalist species survived briefly, but even they faced eventual decline as fires, drought, and soil depletion intensified. The rapid restructuring of plant communities illustrates the speed and severity of the Permian terrestrial crisis, showing that extinction was not only inevitable, but accelerated by compounding stresses. Sedimentary records show repeated pulses of fire, drought, and sediment collapse, a relentless sequence of environmental shocks. Layers of volcanic ash, interspersed with oxidized paleosols and charcoal, provide a temporal map of destruction, revealing how repeated catastrophes prevented recovery. Each pulse erased fragile ecological networks, leaving behind only fragments of the once thriving landscapes. The supercontinent itself became a patchwork of barren zones, burned forests, and lifeless plains, a harsh reminder of Earth's vulnerability to extreme planetary change. From scorched forests to barren floodplains, the terrestrial world teetered on the brink of ecological annihilation. Life had become a shadow of its former abundance, struggling against fire, drought, toxic soils, and cascading food web collapse. The balance of ecosystems, carefully maintained for tens of millions of years, was irrevocably broken. In these ashen landscapes, the next stage of the Permian extinction would unfold, sweeping away the last refuges of life on land and leaving the planet's surface a near-empty tableau. The remnants of forests, bones, and fossilized footprints whispered the final echoes of terrestrial life before total collapse. From burning landscapes to the shattered balance of ecosystems, Earth had entered its darkest chapter. Life clung desperately to the last fragments of habitat. Each survival a fleeting defiance amid scorched soils, dried rivers, and collapsing food chains. As the planet approached the near-complete annihilation that would erase 98% of its inhabitants, the collapse of the food web, the last green shoots struggled beneath a sun veiled in ash, barely sustaining life. Scattered pockets of vegetation, reduced to stunted forms, clung to survival in isolated soils, yet even these sparse refuges could not support the herds that once roamed freely. Dicynodonts and other herbivorous synapsids wandered scorched plains and dried floodplains, their search for sustenance increasingly desperate. Fossilized leaves and stems, already diminished by fire and drought, now represented the final remnants of primary production, a fragile thread holding together entire ecosystems. Without these photosynthetic anchors, the chains of life above and below began to unravel. Herbivores scoured barren landscapes, their numbers dwindling with every failed season. Bone evidence shows stunted growth and interrupted ontogeny, signaling chronic malnutrition. Populations became fragmented, with isolated groups struggling to maintain reproductive viability. Paleontologists have traced these patterns across continents, revealing synchronous collapses in regions as distant as Siberia, China, and South Africa. Every failed feeding season further accelerated the descent toward extinction, as surviving herbivores consumed what little remained of the ecosystem. Predators prowled empty plains, encountering hunger where abundance once reigned. Fossilized gorgonopsians, therocephalians, and other carnivores show signs of emaciation and skeletal stress, reflecting the scarcity of prey. Hunting ranges expanded, forcing predators into areas already devastated by fire and drought. Interactions that once maintained balance, predator and prey dynamics, now became desperate struggles for survival, with starvation replacing ecological equilibrium. The collapse of one trophic level rippled upward, leaving top predators teetering on the brink of disappearance. Fossil evidence reveals stunted growth, skeletal deformities, and starvation marks in surviving animals. Isotopic analyses of carbon and nitrogen in bone collagen indicate nutritional stress, while microfractures and lesions point to weakened physiology. In both terrestrial and marine species, evidence of chronic malnutrition is pervasive, highlighting that even survivors bore the scars of this global crisis. Life persisted only as a fragile shadow of its former abundance, with every organism teetering between endurance and oblivion. Microbial infections spread unchecked as weakened populations fell victim to disease. Pathogens exploited compromised immune systems, accelerating mortality in herbivores and carnivores alike. Paleopathological studies identify lesions, bone deformities, and microbial traces in fossils from multiple continents, revealing that disease became a potent secondary agent of extinction. In ecosystems already stripped of complexity, infections contributed decisively to the breakdown of remaining populations, leaving only the hardiest or luckiest species in fleeting refuge. Sudden extinctions appear in the fossil record, a testament to the fragility of interconnected life. Insect, amphibian, and vertebrate assemblages all show abrupt disappearance horizons, highlighting the domino effect of ecological collapse. Even species that had survived earlier, environmental stresses were not spared, as the extinction cascade consumed every link in the web of life. Fossil layers record these events with remarkable synchronicity, showing that the unraveling of food webs was rapid, global, and relentless. Soil and water analyses indicate nutrient depletion, preventing even resilient plants from rebounding. Nitrogen, phosphorus, and potassium cycles were disrupted by acidification, sediment loss, and volcanic inputs, leaving remaining flora unable to restore the primary base of the food web. Rivers that once transported nutrients to floodplains carried nothing but acidic runoff and sediment-laden water, further starving terrestrial and aquatic ecosystems alike. This systemic nutrient collapse amplified trophic stress, ensuring that even isolated survivors faced a barren and hostile world. Herbivorous synapsids left tracks that abruptly end, fossils capturing life interrupted mid-struggle. Trackways preserved in mudstone show sudden termination, implying death or forced migration that failed. Similar patterns appear in amphibian burrows and nesting sites, suggesting that many species perished while seeking refuge or food. These frozen moments in time illustrate not just extinction, but the abrupt, violent, and inescapable nature of the Permian crisis. Marine predators faced parallel crises, their food sources collapsing as plankton and reef systems vanished. Fossilized fish and early marine reptiles show stunted growth, empty stomachs, and mass mortality layers corresponding to terrestrial die-offs. Oceanic food webs, already weakened by anoxia and acidification, could not withstand further depletion of primary producers, linking marine and terrestrial collapse in a planetary chain of ecological failure. The planet's biosphere was contracting from every angle, leaving only scattered survivors struggling to persist. Interdependence became a curse, as the loss of one species triggered multiple collapses across trophic levels. Every extinction reinforced the next, a chain reaction cascading across continents, ecosystems, and habitats. Specialist species vanished first, followed by generalists that relied on a network of interdependent life. Food webs, once resilient, were reduced to fractured fragments, unable to support even the most adaptable organisms. The collapse of interconnections amplified vulnerability and magnified the speed of global extinction. Paleontological models show fragmentation of populations into isolated refuges, unable to maintain genetic diversity. Surviving individuals persisted only in microhabitats, shielded from the worst environmental extremes. Yet these refuges were small and unstable. Reproductive isolation and limited gene flow created bottlenecks that made populations increasingly fragile, highlighting the long-term consequences of ecological collapse beyond immediate mortality. Life endured, but in a form so constrained it was vulnerable to the next pulse of planetary catastrophe. From the smallest plankton to the largest gorgonopsian, the pulse of life faltered across every ecosystem. Energy flows ceased, nutrient cycles stalled, and interactions that had sustained complex communities were broken. The biosphere, once teeming with millions of species, was reduced to a shadow world, struggling to maintain the delicate balance that had allowed life to flourish. Even the survivors carried the scars of collapse, physical, ecological, and genetic, a testament to the planet-wide unraveling of life's intricate web. The final echoes of living systems, from desiccated plains to silent seas, whispered of a world unraveling. From biological collapse to the pulse of Earth's climate gone mad, ecosystems no longer functioned, and every surviving organism teetered on the edge of oblivion. Forces of heat, poison, and starvation converged relentlessly, driving the planet toward the catastrophic day when 98% of life would vanish, leaving Earth a barren and transformed world. Fever planet. The air thickened with carbon dioxide, an invisible mantle trapping unbearable heat, turning once fertile landscapes into an oven. Sunlight filtered through a haze of volcanic gases and smoke, warming the ground to scorching temperatures and baking soils already depleted by fire and drought. Even hardy plants that had survived the collapse of forests now wilted under relentless heat, their photosynthetic machinery failing as carbon saturation escalated. Fossil evidence from paleosols indicates temperatures rising far beyond previous norms, a planetary fever accelerating the final stages of terrestrial extinction. The atmosphere itself became a predator, suffocating life and leaving only pockets of temporary refuge. Oceans shimmered with superheated water, steam rising in ghostly columns across the equator, distorting horizons that had once supported thriving marine ecosystems. Conodont and brachiopod oxygen isotopes reveal sea surface temperatures reaching unprecedented extremes, while evaporite deposits mark repeated cycles of water loss and chemical concentration. Coral and ammonoid reefs disintegrated, leaving skeletons embedded in mineral-rich sediment, remnants of ecosystems incapable of sustaining life. Currents, once steady conveyors of nutrients and heat, became chaotic, spreading thermal stress and chemical toxicity across the oceans. Polar ice melted into oblivion, removing the last stabilizing elements of global climate. Glacial deposits vanish from Permian strata, replaced by sediments indicating torrid conditions even at high latitudes. Sea level rose sharply, flooding lowlands, while superheated waters evaporated faster than rainfall could replenish them. Seasonal gradients flattened, winds intensified, and deserts expanded into formerly temperate regions. Fossilized plants in paleo-latitudes near former ice margins show stress markers consistent with extreme heat and drought, evidence that no corner of the planet remained untouched. Fossilized sedimentary structures reveal layers baked under unprecedented heat, a record of planetary fever written in stone. Volcanic ash layers, interspersed with oxidized soils, indicate repeated pulses of thermal extremes. Carbon isotope excursions trace spikes in atmospheric CO2, coinciding with these pulses, confirming a link between tectonic activity and runaway greenhouse conditions. Paleoclimatologists reconstruct a world in which temperature oscillations were violent and unpredictable, leaving life with little time to adapt or migrate. Volcanic eruptions continue to pump sulfur and carbon into the atmosphere, amplifying the greenhouse effect and creating a toxic, acidic haze. Aerosol and sulfur deposition contributed to acid rain, further stressing terrestrial and marine life already weakened by starvation and drought. The Siberian traps released immense volumes of lava and gas, flooding regions with heat and chemical stress. Combined with previously destabilized soils and oceans, these eruptions reinforced a self-perpetuating cycle of ecological collapse and planetary heating. Paleotemperature proxies indicate global averages soaring beyond 40 degrees Celsius, with equatorial regions far hotter. Fossil evidence shows adaptations among surviving species, burrowing behaviors, nocturnal activity, and refuge in shaded or aquatic microhabitats. Yet even these adaptations could only delay the inevitable. Physiological limits were breached in many taxa, leaving mass mortality layers preserved in sedimentary records. Thermal stress was absolute, sparing almost no organism outside highly localized refugia. Marine thermometers inferred from oxygen isotopes record ocean surface waters boiling in shallow seas. Dissolved oxygen plummeted, leading to anoxic events that suffocated remaining marine life. Coral reefs, trilobites, and brachiopods vanish from successive strata, replaced by microbial mats and bacterial carbonates. Even deep-sea organisms, once buffered from surface extremes, experienced catastrophic changes in temperature, salinity, and chemical composition. The oceans, which had supported life for hundreds of millions of years, now became a crucible of death. Wind patterns shifted violently, creating deserts and droughts across continents previously lush and fertile. Atmospheric circulation destabilized as the planet heated, leading to extreme storms alternating with long, arid intervals. Volcanic particulates and greenhouse gases interacted with solar radiation, producing a scorched, turbulent atmosphere. Sedimentary layers reveal these wind-driven processes, with sandstones and loess deposits marking deserts that expanded at unprecedented rates. Terrestrial ecosystems were fragmented, leaving survivors isolated in shrinking refuges. Carbon isotope excursions trace pulses of volcanic CO2, mirroring the timing of mass extinctions on land and sea. Each pulse reinforced warming, triggering methane release from destabilized clathrates and amplifying heat further. The feedback loops were rapid and catastrophic, leaving life increasingly unable to adapt. Modeling of these cycles shows the near impossibility of survival for large-bodied organisms dependent on complex ecosystems, while small, adaptable species persisted only in extreme microhabitats. Even the most extreme survivors were forced into micro-refugia, clinging to cool pockets or deep subterranean burrows. Fossils of small amphibians, burrowing synapsids, and select invertebrates hint at desperate strategies to escape the full force of the fevered planet. Evolutionary pressures favored miniaturization, burrowing behavior, and thermal tolerance, shaping the lineage of survivors for the post-extinction world. These isolated populations became the last flickers of life on a planet consumed by runaway greenhouse conditions. Geochemical markers show repeated spikes in methane release, reinforcing a runaway greenhouse cycle that sustained extreme global heating. Isotopic analysis of carbon and sulfur demonstrates recurring feedback loops, each intensifying temperatures and stressing ecosystems further. These geochemical fingerprints link volcanic activity, oceanic chemistry, and atmospheric composition in a catastrophic web that Earth's biosphere could not escape. From searing tropics to barren poles, the fevered planet left only fragments of habitable zones. Micro-refugia persisted as desperate sanctuaries, but their inhabitants were few fragmented, and highly vulnerable. The planet had reached a climax of thermal and chemical extremes, a world in which survival was the exception, not the rule. The few forms of life clinging to existence, hidden in shadows or burrows, whispered of resilience amid apocalypse. From heat and desolation to the last flickers of survival, Earth had become a fever planet, a crucible in which life's endurance would be tested to its limits. Life persisted only in isolated refuges, each fragile existence a testament to resilience, even as the planet hurtled toward the cataclysm that would erase 98% of its inhabitants and leave Earth profoundly transformed. The survivors in the shadows, hidden within the scorched surface, shadows became sanctuaries for the living, spaces where the planet's fury softened enough to allow fragile life to persist. In a world of blistering heat, acid rains, and desiccated soils, only the most concealed pockets offered shelter. Subterranean burrows, deep caves, and shaded fissures became the theatres of survival, where tiny reptiles, amphibians, and invertebrates eked out existence. Evidence from these refuges reveals microhabitats with stable temperatures, reduced exposure to toxic gases, and intermittent access to water-critical conditions for persistence in the wake of global catastrophe. Caves and burrows offered protection from relentless heat and toxic air, shelters carved by both geology and instinct. Sediment infill and mineralized burrow walls preserved the outlines of these temporary havens, showing how life took advantage of every nook and crevice. Fossilized trackways, burrow networks, and preserved remains indicate small vertebrates moved carefully through these microhabitats, avoiding open terrain where death awaited. Survival here required a combination of instinct, adaptation, and luck, and only a fraction of pre-extinction species endured in these confined refuges. Tiny reptiles, no longer predators but survivors, persisted in microhabitats overlooked by catastrophe. Miniaturized synapsids and small diapsids appear in the fossil record with stunted growth, reflecting both limited resources and evolutionary pressure towards survival efficiency. Behavioral adaptations, such as burrowing and nocturnal activity, allowed them to exploit niches inaccessible to larger, more vulnerable species. Evidence of limited skeletal stress suggests that these strategies permitted reproduction in isolated populations, creating the first footholds for post-extinction recovery. Remains of small amphibians and synapsids reveal stunted yet resilient lineages enduring in isolation. In regions corresponding to modern-day Russia, China, and South Africa, skeletal remains show limited size ranges and delayed maturation, signaling chronic resource scarcity. Amphibian burrows, often clustered near ephemeral water sources, indicate localized survival strategies that allowed small populations to persist despite global ecological collapse. These isolated lineages would become critical players in the eventual rebound of terrestrial ecosystems. Deep oceans, insulated from atmospheric extremes, hosted microbial communities thriving in low-oxygen refuges. Even as surface waters boiled, subsurface environments provided stable temperatures and chemical conditions sufficient for life. Stromatolite beds, bacterial mats, and microfossils from these depths indicate that microbial ecosystems remained remarkably resilient, maintaining nutrient cycling while larger organisms perished. These oceanic sanctuaries acted as the genetic reservoirs for marine life that would repopulate the seas once conditions moderated. Chemical signatures in sediment cores capture pockets of life, their traces revealing prolonged survival. Isotopic ratios of carbon, sulfur, and nitrogen highlight areas where life persisted despite extreme temperatures and toxic conditions. Layers of organic carbon and preserved microbial mats indicate not only survival but active biogeochemical activity, providing essential nutrient foundations for remaining vertebrates and invertebrates. These chemical fingerprints tell a story of quiet resilience amid planetary desolation. Some lineages adopted nocturnal habits, burrowing or scavenging to navigate a world of extremes. Trace fossils suggest that surviving species altered their activity patterns to avoid lethal daytime heat, venturing only under the cover of darkness. Feeding strategies became opportunistic. Small herbivores grazed on limited vegetation, while carnivores scavenged remnants, each adaptation improving odds of survival in a world stripped of abundance. Evolution favored flexibility, efficiency, and stealth, shaping the trajectory of species that would repopulate Earth. Refuges were often temporary, but recurring survival points allowed lineages to persist across decades. Shifting environmental conditions periodically rendered burrows dry, caves flooded, or subterranean rivers acidic, yet life adapted by moving between microhabitats. These transient sanctuaries, documented by layered sediments and preserved burrow systems, reveal that persistence depended on both mobility and the ability to exploit ephemeral stability. Survival was not passive. It was an ongoing negotiation with a capricious, fevered planet. Fungal and bacterial mats stabilize soils and waterways, creating micro-ecosystems for small vertebrates. Decomposers became essential allies, recycling nutrients in otherwise barren landscapes. Evidence from sedimentary layers indicates that these mats helped retain moisture and provided microhabitats for invertebrates, which in turn supplied food for tiny vertebrates. These interactions, simple yet profound, underscore how life's smallest components sustained the spark of resilience when larger ecosystems had collapsed. Genetic bottlenecks marked these populations, but mutations and adaptability kept the spark of life alive. Surviving lineages, isolated and reduced in number, carried limited genetic diversity, yet selection pressures fostered traits suited for extreme conditions. These adaptations included heat tolerance, water conservation, and behavioral modifications that allowed persistence. Molecular clock estimates suggest that many lineages that survived in microrefugia gave rise to the post-extinction biodiversity that would gradually restore ecosystems over millions of years. Isolated ponds and subterranean rivers became vital habitats, preserving life while the planet's surface remained inhospitable. Water sources buffered against temperature extremes, provided oxygenated refuges, and supported the limited plant life that remained. Fossilized amphibians and small reptiles are often found near these features, confirming that even minor environmental advantages could determine survival outcomes. Such refuges functioned as life's last bulwarks, bridging the gap between cataclysm and renewal. Across microbial mats to tiny burrow-dwelling reptiles, the tenacity of life endured against staggering odds. These hidden survivors were the progenitors of future ecosystems, carrying genetic information and adaptive traits that would shape the trajectory of life on a recovering Earth. Even in the face of near-total annihilation, life's persistence demonstrates the remarkable capacity to endure, adapt, and ultimately reclaim the planet. The last flickers of living ecosystems whispered a promise of resilience. From endurance to the fragile persistence of life, these microhabitats preserved the final survivors, each organism a testament to survival amid catastrophe. Though battered and diminished, life clung to existence, setting the stage for the final struggles of the planet's remaining giants as Earth reached the brink of total collapse. The last of the giants, shadows of colossal limbs stretched across desiccated floodplains, trembling under skies heavy with ash. Rivers, once arteries of life, had shriveled to narrow threads, their waters poisoned by volcanic gases and acid rain. Across these barren landscapes, the largest terrestrial and aquatic creatures moved sluggishly, their immense bulk now a liability in a world that no longer accommodated giants. Every step demanded extraordinary energy. Every breath carried the toxic weight of a suffocating atmosphere, and every moment brought them closer to the irreversible embrace of extinction. The oceans, once teeming with apex predators, became graveyards beneath a boiling surface. Massive nothosaurs and ichthyosaurs, rulers of the Permian seas, flailed weakly in waters stripped of oxygen, their once efficient hunting strategies rendered futile by extreme temperatures and chemical upheaval. Coral reefs had vanished, and primary productivity had collapsed. Phytoplankton blooms were sporadic, decimated by acidification and stagnation, leaving the food web fractured and unstable. Predators starved not from lack of skill but from the disappearance of prey, a cascade of mortality tracing the collapse of an ecosystem built over millions of years. Heatwaves rose from parched soils, bending rivers and scorching the last grazing grounds. Large herbivores, from giant pariasaurs to massive dicynodonts, struggled to find edible foliage among the ash-laden remnants of forests. Glossopteris and other plant lineages, already reduced by fire and atmospheric toxicity, provided little sustenance. The once dominant herbivores, so pivotal to nutrient cycling and seed dispersal, now moved as ghosts of their former abundance, their weakened forms unable to sustain themselves or the predators that relied upon them. A gorgonopsid struggled through the poisoned air, its respiration laboured, its fate sealed not by predation but by environmental collapse. Apex predators that had once hunted with precision now faced prey scarcity, heat stress, and toxic atmospheres that compromised cardiovascular and neural function. Fossilized rib cages indicate repeated stress fractures and pulmonary damage consistent with oxygen deprivation, suggesting that even the most fearsome carnivores succumbed quietly to the slow suffocation of the planet's ecosystems. Dominance in life offered no immunity against a world undone by chemistry, climate, and cataclysm. In sediment layers across Pangaea, the bones of mass mortality assemblages reveal simultaneous deaths on an unprecedented scale. Across the Karoo Basin in South Africa and the Russian platform, sprawling fossil beds show hundreds of skeletons of giant synapsids and temnospondyls entombed together, many preserved in lifelike postures as if caught mid-stride or mid-swim. Isotope analysis of carbon and oxygen ratios in these sediments reveals rapid shifts in temperature and atmospheric composition, correlating with these sudden die-offs. The synchronicity of terrestrial and freshwater species perishing highlights that the cataclysm struck indiscriminately, a planetary-scale disaster in which size, dominance, and mobility offered no refuge from the lethal convergence of heat, toxic gases, and oxygen depletion. Struggling in hypoxic depths, the largest temnospondyls succumbed, and only empty hollows remained. The freshwater systems that had nurtured amphibian lineages for millions of years now boiled under relentless heat, their rivers choked with sediment and toxins. Fossil evidence from riverbeds and floodplains shows mass mortality assemblages. Articulated skeletons collapsed in place, sometimes still aligned as if mid-swim or mid-stride, frozen eternally by the very processes that ended their reign. The scale and simultaneity of these deaths reflect a planet-wide crisis, a convergence of forces that spared nothing by virtue of strength or size. On shallow marine shelves, once thought refuge, apex predators disappeared, and ghostly reefs remained as silent testimony. Evidence from the Zechstein Basin of Europe and Permian strata in South China shows that large marine predators, including nothosaurs, ichthyosaurs, and apex fish, vanished from shallow seas almost simultaneously with terrestrial giants. Black shales and pyrite framboid concentrations indicate widespread anoxia and hydrogen sulfide accumulation, creating lethal waters even in coastal zones. With apex predators gone, mid-level organisms faced cascading ecological collapse, destabilizing reef ecosystems and leaving ghostly skeletons as the final testament to oceans once rich with complex life. Etched in stone, fossilized trackways recount the final chapters of species that once dominated the land. Impressions of gigantic claws and splayed toes stretch across mudstones, sometimes abruptly ending, revealing where life had faltered. These silent records of movement, paused in time, speak more powerfully than bones alone. They are traces of struggle, of attempts to navigate a landscape transformed beyond recognition. Even massive predators, with speed and strength once unmatched, left trails that ultimately led to death rather than sustenance. Every massive creature now bore the mark of ecological collapse. Their dominance no protection against extinction. Thermal extremes, hypoxic waters, and poisoned air struck simultaneously, creating a perfect storm in which gigantism became a curse. Organisms that had once shaped ecosystems through sheer size and predation pressure were now the first to vanish, leaving behind only their fossils and the echoes of ecosystems that had depended on them. The hierarchy of life inverted. Survival no longer favored the mighty but the adaptable, the small and the hidden. As the giants faded into extinction, an uncanny stillness settled, broken only by the faint movements of smaller survivors. Microhabitats, burrows, caves, isolated wetlands harbored the remnants of life capable of enduring the extreme conditions. Lystrosaurus burrowed beneath scorched plains, microbial mats persisted in shaded pools, and small aquatic reptiles clung to oxygen pockets in fragmented waterways. These refuges, however, were islands amid a sea of desolation. The world that had sustained giants for millions of years was gone, replaced by a planet on the edge of utter silence. The final vestiges of towering amphibians, massive synapsids, and apex marine predators whispered the extinction of dominance itself. From desiccated floodplains to boiling seas, life's grandeur had been reduced to a fragile mosaic of survival, a testament to the relentless efficiency of cataclysm. The deaths of these giants underscored a brutal lesson. In a world reshaped by fire, poison, and climate, size and specialization became death sentences. Yet even in this grim tableau, the persistence of microcosms hinted at a world where life might endure, hidden, quiet, and waiting for the first fragile stirrings of recovery. The giants were gone, leaving a hushed planet where the rules of survival had changed irrevocably. From their deaths emerged a world dominated not by size or predation, but by endurance, adaptability, and concealment. The stage was now set for the last survivors clinging to microhabitats, the organisms that would carry the memory of life into the earliest moments after the Permian apocalypse. The final pulse of life. Amid the blackened soil, tiny colonies of cyanobacteria glowed in isolated puddles, defying the scorched landscapes around them. In ephemeral wetlands, these microbial mats performed the slow alchemy of life, fixing carbon and cycling nutrients in conditions that would have killed larger organisms, Sedimentary layers reveal alternating oxic and anoxic intervals, where oxygen briefly returned to shallow soils, giving these mats momentary vitality. The faint traces of chlorophyll preserved in rock tell a story of resilience against an atmosphere heavy with carbon dioxide and toxic gases, where life persisted only by retreating into the smallest scales. In ponds reduced to shallow, evaporating pools, small crustaceans and brine shrimp scrambled desperately for survival. Fossils from the early Triassic show these tiny survivors thriving briefly in hypersaline waters, exploiting niches abandoned by larger marine species. These creatures endured heat, salinity, and oxygen stress that would have been fatal to most other animals. Their shells and exoskeletons, found in concentrated beds, mark both their survival and the precariousness of their existence. A temporary bloom in a world teetering on extinction. Burrowed deep beneath parched plains, small vertebrates eked out existence in tunnels insulated from toxic air. Lystrosaurus, among the last surviving therapsids, relied on digging to escape soaring temperatures and poisonous atmospheric gases. Osteological evidence indicates robust limbs and reinforced skulls adapted for prolonged burrowing, while isotopic analyses of teeth suggest altered diets as surface plants vanished. In these subterranean refuges, life clung to the edge, dependent on microclimates that insulated against the relentless extremes above. Even in marginal marine shelves, opportunistic invertebrates exploited brief windows of oxygenated water. Shallow seas, preserved in black shales, record tiny mollusks, polychaetes, and arthropods, appearing only in intermittent layers where oxygen briefly returned. These ephemeral ecosystems were fragile, collapsing as hydrogen sulfide accumulated in deeper waters. Fossil assemblages show small predator-prey relationships persisting in microcosms, a brief echo of complex ecosystems that had existed before the Permian's final catastrophe. Sediments revealed fleeting blooms of fungi and bacteria, feeding on detritus left by dying organisms. The fungal spike, recorded globally, marks decomposition on a planetary scale, with fungal hyphae and spores filling sediments where plant and animal matter had perished. Geochemical markers indicate increased carbon flux and localized nutrient recycling, highlighting that even in devastation, life left biochemical footprints. These microbial decomposers became the caretakers of a dying biosphere, sustaining the very last threads of ecological function. Traces left in the sedimentary record whispered of life's final, fleeting persistence before the world fell silent. Burrows, feeding trails, and microbial mats etched in fine-grained sediments provide a delicate roadmap of survival. Even in areas stripped bare by acid rain, wildfires, and heat extremes, these traces suggest that some life continued to interact with the environment in ephemeral refuges. Their presence is a stark counterpoint to the vast extinction surrounding them, showing that even in near total collapse, life does not surrender immediately. Occasional rains carried pockets of survival across scorched plains, creating temporary oases for small creatures. Fossilized paleosols and evaporite layers reveal the episodic availability of water, allowing crustaceans, amphibians, and microbial mats to flourish for weeks or months. Invertebrates hatched, vertebrates foraged, and plants briefly recolonized these isolated zones. Yet the abundance was fleeting. Once water evaporated, the refuges vanished, leaving behind a world more hostile than ever, a harsh reminder that survival had become an exercise in constant adaptation. High above, clouds of ash and sulfur darkened the skies, yet life persisted in hidden microhabitats below. Volcanic aerosols and particulate matter reduced sunlight, dropping surface temperatures slightly in some regions while acidifying soils and waters. Microorganisms and small vertebrates benefited indirectly from cooler microenvironments, retreating to shaded crevices, burrows, or beneath dense microbial mats. The contrast between apocalyptic skies and sheltered refuges created pockets where life lingered, yet these islands of survival were fragile and temporary, dependent on rare, favourable conditions. Rocks carry the fingerprints of life's final pulses, telling tales long after the living forms disappeared. Carbon isotopes reflect sudden drops and spikes, mirroring localized blooms and extinctions, while sulfur isotopes reveal periods of transient anoxia and hydrogen sulfide accumulation. These geochemical footprints, coupled with trace fossils, provide the only testimony that some life endured for a final heartbeat before the biosphere almost entirely collapsed. Even in the absence of large organisms, the planet's record preserves these brief sparks of persistence. Within the oceans and lakes' most peaceful reaches, fleeting blooms bore witness to survival amid chaos. Microbial mats, small crustaceans, and opportunistic fish briefly recolonized shallow waters, creating tiny, isolated ecosystems that thrived for months at most. These refugia, preserved in sedimentary layers, capture the last rhythm of life before the Permian crisis extinguished nearly 98% of species. In these transient habitats, the final pulse of life flickered, leaving a delicate, haunting testimony to resilience in a world otherwise emptied of its vitality. Encapsulated in the deep sediments of a dying Earth, microbes reveal how survival was possible against overwhelming odds. Cyanobacteria and extremophile bacteria formed tightly packed mats, sometimes alternating with layers of clay and volcanic ash, indicating periods of environmental stress followed by brief recoveries. Analysis of carbon and nitrogen isotopes suggests that these microbes engaged in unusual metabolic pathways, including nitrogen fixation under oxygen-poor conditions, sustaining minimal food chains in a world largely devoid of complex life. Their existence marks the final attempt of ecosystems to function, preserving traces of life that would vanish completely within thousands of years. Against the backdrop of extinction, the final flickers of life hinted at survival beyond comprehension. From microbial mats to the smallest burrowed vertebrates, life clung stubbornly to existence, yet the planet itself had been profoundly transformed. In this fleeting chapter of survival, Earth teetered at the edge of total silence, a warning etched into stone and sediment of what it means when life approaches its absolute limits. The long silence. An eerie quiet settled over the planet, broken only by the occasional hiss of volcanic remnants still cooling in the distance. The convulsions of the earth had subsided, leaving behind a world stripped of its vitality. Across vast continental expanses, scorched soils and collapsed forests bore silent witness to the forces that had reshaped life itself. The air hung heavy with heat and chemical residues, a suffocating reminder that the day 98% of life vanished was not a single instant, but a drawn-out symphony of catastrophe. Once alive with trilobites, ammonites, and reef builders, the oceans had turned into stratified graves. Surface waters reflected a sun more merciless than ever, while deeper layers stagnated, starved of oxygen. Hydrogen sulfide accumulated in anoxic zones, seeping into coastal waters, bleaching sediments, and leaving microbial mats as the only visible traces of life. Where coral reefs had once thrived, only skeletal fragments remained, interspersed with black shales recording the planet's toxic chemical legacy. Along the scorched coastlines, Salt-crusted sands bore the imprint of animals that would never return. Footprints of synapsids and amphibians faded into desiccated mud, their fossilized shapes a ghostly testament to creatures struggling against the collapsing ecosystems. Rivers that had once carried nutrients across continents ran shallow or evaporated entirely, leaving behind cracked riverbeds and salt flats. Even the landscapes themselves seemed to mourn, their contours softened by erosion and devoid of the vibrancy of previous Permian biomes. Sediments recorded the final chemical signatures of a world in collapse. Layers of black shale and carbonate revealed extreme anoxia, sulfur accumulation, and elevated mercury levels, tracing the slow suffocation of marine and terrestrial habitats alike. Stable isotope analyses hinted at profound disruptions in the carbon cycle, reflecting the immense stress placed on global ecosystems. Each layer became a page in the record of near-total extinction, capturing the scale and immediacy of the planetary crisis. Even the faintest organisms left their marks in microscopic fossils. Cyanobacteria, halophilic archaea, and tiny invertebrates clung to marginal habitats, preserving a fragile continuity of life amid widespread desolation. Their presence offered a sliver of hope, evidence that even in the wake of almost complete annihilation, life's tenacity endured. Yet these traces were isolated, scattered across thousands of kilometers, and only capable of persisting in very specific environmental niches. Arid plains and scorched forests revealed the absence of primary producers. Glossopteris and other Permian plants had vanished, leaving soils depleted and nutrient-poor. Without vegetation, herbivores had starved, predators had followed, and the intricate web of terrestrial life lay in ruins. Fossilized spores and charcoal remnants hinted at the last fires that consumed the final vestiges of forests, leaving the land barren and exposed to erosion and chemical weathering. Tiny pockets of microbial mats persisted in shallow lagoons and hypersaline pools, their green sheen a rare reminder that life could endure. In some evaporative basins, layers of stromatolites recorded the survival of microbial ecosystems, harnessing light and nutrients where nothing larger could survive. These extreme refuges became the repositories of genetic lineages that would, over millions of years, contribute to life's eventual resurgence. Trace fossils suggested the brief survival of small invertebrates, feeding on decaying matter and moving through sediment layers in ephemeral microhabitats. Worm-like burrows, fossilized traces of scavenging arthropods, and other subtle signs indicated that life clung on where conditions allowed. Each trace was a testament to adaptation and persistence. Small victories in a world otherwise emptied of complexity. Geochemical anomalies revealed a biosphere under unprecedented stress. Mercury spikes, sulfur isotopes, and negative carbon excursions painted a picture of environmental collapse, revealing the chemical fingerprints of volcanic eruptions, global warming, and ocean stagnation. These markers, preserved in rock layers worldwide, allow scientists today to reconstruct the magnitude of this mass extinction event and understand why it remains unparalleled in Earth's history. Spanning continents and ocean floors, dead zones extended for thousands of kilometers, oxygen-depleted basins and scorched terrestrial landscapes formed near continuous belts where life had all but vanished. The biosphere, once thriving, had been compressed into microscopic refugia, a fragile shadow of its former abundance. Ecosystems ceased to function in any meaningful way, leaving Earth suspended in a state of near-total biological stasis. At the most basic level, biogeochemical processes began to collapse. Nitrogen cycling slowed, primary production plummeted and the decomposition of organic matter became a slow, sporadic process in localized pockets. Without the activity of larger organisms, soils eroded and sediments accumulated in unusual patterns, permanently altering the surface of the planet. Each anomaly, each disruption, testified to the severity of the Permian apocalypse and the fragility of the systems that sustain life. Subtle chemical signals embedded in ancient rocks reveal the ghostly presence of life eking out survival. Geochemical markers, such as trace amounts of lipids and isotopically light carbon, indicate that microbial mats and chemoautotrophic communities persisted in isolated niches. These organisms metabolize sulfur, iron, and nitrogen compounds in ways that left fingerprints detectable millions of years later, allowing scientists to map the final, fragmented web of life. Even as surface ecosystems collapsed, these extremophiles maintained microhabitats capable of sustaining genetic diversity, providing a faint but critical bridge between the Permian biosphere and the eventual resurgence of life in the Triassic. Through the darkness of devastation, life endured solely in whispers. Microbes, extremophilic archaea, and a few resilient invertebrates carried on, their metabolic processes slow, fragmented, and isolated. These survivors left traces in sediments, tiny, subtle, almost invisible, marking the last echoes of an ancient biosphere now silenced. The long silence stretched across the planet, an eerie calm that would endure for millennia, waiting for the faintest stirrings of a biological dawn far in the future. A silence unlike any before settled over the planet, a stillness that spoke of life's fragility and the unimaginable forces that can reshape an entire world. In the shadows of desolation, we glimpsed the resilience of life clinging to survival, the delicate thread connecting past and future. Rocks, ash, and fossilized whispers bear witness to a day when Earth nearly died, reminding us that even the mightiest ecosystems are vulnerable. If you are captivated by the hidden dramas of deep time, subscribe for more journeys into Earth's vanished worlds.